Warning: nickel and nickel salts are toxic and irritating. Sulfuric acid is corrosive and its vapor is toxic and irritating. Wear gloves and a mask when handling them. Hi guys, here is NiMH. Batteries are an extremely important component of our daily life, but once they are thrown away, they become harmful wastes that are difficult to recycle. In this video, I'll demonstrate a crude method of recycling nickel and lanthanide elements from nickel metal hydride batteries, or NiMH for short. Those batteries are prevalent as a substitute for the NiCd batteries that contain toxic cadmium but are getting phased out by lithium-ion batteries that have higher energy densities. The first thing to do is opening the battery, preferably when fully discharged. I use a pair of pliers and a pair of tongs to tear off the outer steel casing and expose the inside battery material. You can see that the battery consists of black anodes containing nickel hydroxide, a steel mesh, and paper diaphragms loaded with the cathode material, which is an alloy of nickel and lanthanide elements. I then soaked everything in water for 3 times to remove the potassium hydroxide electrolyte. At the end of the third wash, the pH of the water is about 8, so most of the electrolyte is removed. The battery material is removed into another beaker and weighs 25.6 grams. Then I weigh out 100 grams of 37% sulfuric acid, which will leach the nickel compounds into solution. Note that this is a rather large excess, and 75 grams of acid would work as well. The sulfuric acid is then poured into the beaker with the battery material. At first, nothing happens as nickel hydroxide reacts slowly with sulfuric acid at room temperature. Therefore, I place the beaker on a hot plate to speed things up. You can see the acid is turning green, and some bubbles begin to evolve. The nickel lanthanide alloy is reacting with sulfuric acid to produce nickel sulfate, lanthanide sulfates, and hydrogen. The nickel hydroxide also reacts with the sulfuric acid to give nickel sulfate. The battery may also contain some nickel hydroxide oxide from incomplete discharge, which also dissolves in sulfuric acid, but it releases oxygen instead of hydrogen. Finally, the metal mesh is made of stainless steel, which dissolves in acid to produce ferrous sulfate, nickel sulfate, and chromium sulfate. Soon, the reaction turned much more vigorous and huge amounts of gases are released. I quickly removed the beaker from the hot plate to not let boiling acid spray out, and fortunately the reaction did calm down. As you can see, a ton of choky acid fumes are released along with the hydrogen gas, so make sure to place a petri dish above the beaker to condense the fumes. There are still a bunch of black nickel hydroxide remaining, so I heated the acid again to completely dissolve them. The solution already gained a very deep green color due to the nickel ions, and if you look closely at the bottom of the beaker, there are some precipitates that are lighter in color. This is the lanthanide sulfate formed in the reaction, which crashed out due to its small solubility in boiling water. It seems a lot, but actually isn't a very big amount, so I don't think it is worth recovering unless you're recycling batteries on a very large scale. After most of the black stuff disappeared, I used a pair of tweezers to remove the shiny metal mesh, as well as some porous anode materials and the paper diaphragm. The combined weight of those battery materials after the sulfuric acid leaching is 8 grams, which means that there are 17 grams of nickel in the solution. Upon inspecting the anode material closely, you can see that it is made of a plastic foam that has a large surface area, which can support the nickel hydroxide and enhance its reactivity. I suction filtered the solution when it is still hot. Here you can clearly see the white precipitates at the bottom of the beaker. The residue on the filter paper is the remaining battery materials as well as the lanthanide sulfate precipitate. The filtrate displays a dark green, almost black color, and we're going to crystallize our nickel sulfate from it. The solution is evaporated in a crystallizing dish and removed from heat when its volume reduces to around 50 mL. When it cooled the next day, you can see the beautiful dark green crystals of nickel sulfate heptahydrate crystallizing out from the mother liquor. They're not exactly transparent, but I can grow beautiful single crystals from them. Those crystals are filtered and dried on a piece of filter paper. The final yield of nickel sulfate heptahydrate is 29.32 grams, representing a yield of 64.5% with reference to the 17 grams of nickel hydroxide dissolved in the acid. There are still some nickel in the mother liquor, but unfortunately I spilled it on my lab table, so never mind. Still, I'm totally satisfied with the amount of product that I have, and I'm now ready to perform some experiments such as electroplating with it. See you soon!